Today, I will be discussing research being done at UW into how blind users interact with artboards. The research was being conducted by the University of Washington Create Lab and presented at the Conference on Human Factors in Computing Systems in 2021. The problem this research seeks to explore is that digital artboards such as PowerPoint, Google Slides, and Apple Keynote are everywhere in modern workplaces. Being able to comprehend and manipulate them is required in academic and professional settings at all levels. In the research, UW Create Lab is identifying usability of artboards by blind people using a screen reader at tasks related to content comprehension and content manipulation. The research seeks to identify themes from blind users and explore potential solutions for them.
Understand the needs of and issues faced by blind users of artboard programs, we conducted a mixed method study in two phases with 15 total participants. In the first phase, we conducted contextual interviews and observations with 12 participants. In the interviews, we asked participants about their experiences with artboard programs and then observed them creating a digital presentation about their favorite book or animal using their preferred program. They were asked to think aloud as they made the presentation. The second phase was a task-based usability study of 12 participants, 9 of whom participated in the interviews. During the study, participants performed two sets of tasks. The first set dealt with content interpretation, and the participants had to answer questions about the artboard shown at the beginning of this video. The second set dealt with content generation, and for these tasks, participants were asked to place and manipulate objects on an artboard. Participants were timed while performing the tasks and were asked to stop after 5 minutes.
This research contributes to the knowledge of accessibility and interaction designers on how well common artboards are able to be used by blind users with a screen reader. Themes and potential solutions that were identified from this research include no feedback when objects are changed, which would be solvable by improved accessibility features that communicate changes, high cognitive load when artboards are used by blind people with screen readers, which could be solved by implementing features that allow for glanceability. Perceived fragility of artboards by blind users, meaning that they feel that the state can be changed without intending to. This can be solved by designing artboards that are more robust when used with a screen reader and do not make changes without the user's intent. Now we will take a deeper look into the findings that I just summarized. The first half of this research project is focused on how effective blind screen reader users are at identifying elements on an artboard. The figure includes both full and partial successes, where a full success means the user could identify the item and could confirm that they successfully identified the item without an intervention. Partial success means that the user identified the item but could not confirm for themselves if they were successful or not. Some tasks that users performed very well at were identifying which objects were on the slide and what text is in the text box. Most other tasks have far lower success rates, with one task being unsuccessful for all users. The task involved determining the direction of an arrow. This arrow is a right arrow rotated 90 degrees so it is pointing up. Most users believed it was pointing to the right since the name said right arrow. One user was even close to getting it right, mentioning that two researchers, when scanning the page for all elements, that the arrow was not in fact pointing to the right. However, when it was time to answer this question, the user had forgot due to high cognitive load. In this video, the artboard used for identifying success of interpreting objects is described by a screen reader. Note how much information is given about each element and imagine how hard it would be to keep track of this information mentally.
To illustrate this, the following is a screen reader describing objects on an artboard in Microsoft PowerPoint. The artboard has a green circle next to a red rectangle with the words Hello World on it, and to the right of them on the bottom edge of the artboard is a black arrow pointing up.
Text frame hello, world. Right arrow. Rectangle obscured. Oval. 164 points from top slide edge, 297 points from bottom slide edge.
The second half of this research project is focused on how effective blind screen reader users are at manipulating elements on an artboard. The figure includes both full and partial successes, where a full success means the user could manipulate the item and could confirm that they had successfully manipulated the item without intervention. Partial success means that the user manipulated the item successfully but could not confirm for themselves if they were successful or not. For manipulation, there was a more even distribution of success across tasks. However, it is notable that the most successful task was typing in text into a text box. The least successful tasks were moving shapes, to a specific position and moving a shape to overlap another shape. In the case of moving a shape to a specific position, one difficulty is users not knowing how large the artboard is in pixels, since all measurements provided by the screen reader are in pixels. Users did not know if the element they moved was on the board or off the board. Moving shapes to overlap each other also had a low success rate because the screen reader would announce that shapes were overlapping as soon as their bounding boxes were touching. However, this did not mean that the shapes were visually overlapping. In the next part of this presentation, I intend to present in greater detail the themes identified by researchers for usability of digital artboards by blind screen reader users. A theme researchers identified when conducting user research on blind people using digital artboards was that the artboard does not provide sufficient feedback when a user completes a task. Because screen reader users cannot determine if their change was successful without reading the element again, this causes high cognitive load and reliance on sighted peers to review changes on artboards for blind users. A lack of autonomy for blind users when using digital artboards was another theme that came up during usability testing, but did not make the list of top themes for this research. Many users indicated that they would be very excited if they could use artboards autonomously to create presentations for both sighted and blind peers. Another theme that came across through the research is high cognitive load experienced by blind users when both interpreting and manipulating artboards. A screenshot of using Microsoft PowerPoint is provided, which shows how much information is coming at blind users when they attempt to make simple manipulations using this app. Many users expressed frustration that absolute pixel units were given, with one user asking, "How many pixels big is the slide?" Most users expected the elements of an artboard to be read from left to right, but unfortunately, all artboard software tested provided the elements in the order that they were placed on the artboard, also known as the Z order. A PowerPoint-specific issue shown in the figure is that the screen reader user could have menu items hidden from them until they expand the ribbon to a specific tab, making navigation of features harder for screen reader users. Microsoft creates hotkeys for screen reader users as a workaround for this issue, but it requires that a person memorizes dozens of keyboard shortcuts just to use one app. As one subject said, designers assume that blind people have an elephant memory, and later said that memorizing things is an unfortunate expectation of blind people. The last major theme identified by researchers is a result of the first two themes, high cognitive load and a lack of feedback in result of perceived fragility of artboards by blind users. Many users in this study express anxiety when interpreting artboards that have edit permissions because they worry about making unintentional changes to the artboard. This is also the case when manipulating an artboard. As indicated by the example on the right in this slide, where a user attempted to change a triangle color to red using Microsoft PowerPoint, the user attempted to use the shape fill feature to change the color to red, but did not know that the button they chose filled it with the default color without announcing the change. The user later identified the triangle was orange and attempted to change it to red by using a keyboard shortcut. However, the keyboard, without announcing, changed the focus from the triangle to the background and opened a pane to format the background. The user proceeded to change the background color to red and believed that they had successfully changed the triangle color to red, since this change was not announced. A solution to this problem would be for the artboard to announce changes to screen reader users to increase perceived robustness. In conclusion, the most popular artboards are not well designed for use with screen readers due to poor design choices. These screen readers create high cognitive load and perceived fragility among blind artboard users. Let me try that again. Better accessibility tools would allow screen reader users glanceability to read artboard objects from left to right and to have relative position measurements. Announcing changes to screen reader users would make artboards more robust as well as glanceable. Additional research has been conducted that resulted in a Chrome extension that allows blind users to have this experience with Google Slides in a browser, and it is linked on this slide. Thank you for watching my presentation. A question I have for you to take away is, What tools would you use to make artboards more accessible now that you know about issues that blind users face with them?